Hi everyone. So over the last couple of weeks, we've learned a lot of different methods for evaluating integrals. And so in this video, we're not going to talk about any new methods. We're basically just going to review all the different methods we have, as well as discuss, how do you know when to use which method? So, so far, because we've been focusing on one integration method at a time, it's been pretty clear on the homework, or on a quiz or something like that, which method you're supposed to use. But from here on out, I'm not going to tell you every time, okay, this is a trig substitution integral, or this is an integration by parts integral, or anything like that. You'll be expected to look at an integral and kind of figure out which method you have to use. So I want to go through basically kind of a step-by-step list of steps you can take to try to figure out which method to use. And one thing I just want to say before I even get started, and this is something I know I've said a lot, but this list only really goes so far. There is definitely an aspect of trial and error that happens with integrals, and especially with tricky integrals. I think integration is, in a way, it's almost kind of a creative thing, because in some cases, there's going to be a pattern that you've seen before and you know how to do, but in other times it really is a matter of being comfortable with trying something, seeing if it works, and if it doesn't, trying something else. So keep that in the back of your mind, even as we kind of try to lay out these clear steps and rules that sometimes you have to kind of break away from this list and just try things. Okay, so first thing on our list is going to be to basically look at a table of known integrals. So this is the list of integrals that I will give you on, like a test. And so anything that's not on this list, you will be expected to use the other strategies to integrate. And I just want to mention that because, some, like if you just Google, integration table or something like that, you might find a list that includes other things. But for this class and for like tests, I would expect that these are really the only ones that you're allowed to just kind of say what the answer is without putting in any work. So again, first step is basically to check an integral table and see, is the thing I'm trying to integrate one of the things on this list? Okay, so let's say that does not work. So the next thing you want to try is you want to try to simplify the integrand if possible. So I want to show you a couple of examples where that really is a key step, where if you were to try to just sort of plow ahead with a method, you would get kind of stuck. But if you pause and try to simplify, you'll be able to actually evaluate your integral. So one example would be something like the integral of x squared plus the square root of x over x dx. So we saw examples like this at the beginning of the quarter. This is one that you would want to split up into two fractions, right? So you would say, okay, it's going to be the integral of x squared over x plus the square root of x over x. And then you could simplify each of those. So that would be the integral of x plus, so here we would have x to the 1/2 divided by x to the 1. So that's going to be x to the negative 1/2. And then from there, you can just use the reverse power rule. So by the way, in this video, we're going to do a lot of examples, some of them kind of along the way of making this list. And then at the end, we'll do some other examples. For the most part, we're not going to completely finish off these integrals because this video is more just about identifying what method to use and less about, the nitty gritty of doing the actual algebra and getting your answer. Okay, so another example where simplification is essential would be tangent of theta over secant squared of theta. So this one kind of looks like maybe you could do a substitution, but the problem is that the derivative of tangent is secant squared, but that's in the denominator. So if tangent and secant squared were flipped, then you could use substitution, but because the secant squared is in the denominator, the substitution is just not going to work. You could try it, but you'd see that it doesn't work. So instead what we want to do is we want to rewrite each of these in terms of sine and cosine. And that's a general kind of good strategy to have in mind with with trig integrals, is to see, can I rewrite everything in terms of sine and cosine and simplify from there. So this is going to be the integral of sine of theta over cosine of theta times cosine squared of theta over 1. And so from here, we can cancel out a cosine of theta and a cosine squared there. And then now we're left with the integral of sine of theta times cosine of theta d theta. And so that is one of the ones that you can evaluate using trig identities. So you could rewrite this as 1/2, or maybe I'll say it this way, the integral of 1/2 times sine of 2 theta d theta. And then from there, it would just be a simple substitution, like one of the substitutions that you might be able to just do in your head. Okay, so the next thing you want to do, so let's say that simplification isn't really getting you anywhere. The next thing you want to look for is a substitution, not trigonometric substitution, just like a regular substitution. So an example of, how that might look. So we've talked about this a good amount, but typically a substitution might involve something in your integral that is like maybe a little bit more complicated, but then which also contains the integral also contains the derivative of that more complicated thing. So an example of that might be an integral like the following. So if you have the square root of sine of x times cosine of x dx. So if you let u equal sine of x, then du is going to be cosine of x dx. And so you'll be able to rewrite this integral as the integral of the square root of u du. Another integration or another example that involves substitution that maybe is like a little bit harder to spot would be something like this. So let's say you're evaluating the integral of x cubed over the square root of 1 plus x squared. So this is one that you actually could do with trigonometric substitution, which we'll talk about in a few minutes, but this is one you could do with substitution as well. So what would the substitution be here? Well, if we let u equal 1 plus x squared, then that means that x squared is equal to u minus 1. And then du is going to be equal to 2x dx. So why is this going to be useful? Well, basically, together between this fact and this fact, those two things together are going to take care of this x cubed. And sorry, I forgot a dx for some reason here. So what would this end up looking like? Well, after you do the substitution, we would have x cubed over the square root of u times times du over 2x. And so this x here would get rid of one of these x's, and then you could rewrite the x squared in the numerator as u minus 1 squared. And then from here, you could just evaluate it by expanding the numerator and splitting up the fraction as we saw in an earlier example. Okay, so that's substitution. So let's say that you can't find a substitution and you also can't do any simplification, you're kind of stuck with either of those methods. That's when you now want to think about different types of functions and the methods for those types of functions. So we're going to go through and basically talk about all the different types of functions that we've encountered and how to deal with each of them. So let's say that you have a trigonometric function. So typically, if it's a very simple trigonometric function, then you might be able to evaluate it just using, the integral table or maybe like a simple substitution. But this is more kind of complicated trigonometric functions. So one type of format that we've seen is that if you have an integrand that looks like sine to the m of x times cosine to the n of x, or tangent to the m of x times secant to the n of x. You're basically going to use trig identities and substitution. And so this is, we talked about this in a few videos ago. Basically, you're looking at whether the exponents are even and odd and using that to figure out what makes sense in terms of your substitution. If you have a trig integral that's not of one of those forms, then basically you're going to have to use trig identities. So an example of that would be something like sine of theta times cosine of theta, which we talked about up here, right? So if you have sine of theta times cosine of theta, it is technically of the form sine to the m times cosine to the n, but if you read through those rules, it doesn't. So an example of where you could use a trig identity might be something like sine of theta times cosine of theta, right? You could rewrite that as 1/2 times sine of 2 theta. Or other examples that we've seen using trig identities are things like sine squared of theta or cosine squared of theta. Those are other examples where you have to use trig identities. All right, so another kind of function that we've encountered in this class is a rational function. So a rational function is a function that is a polynomial divided by another polynomial. So there's a few different things you want to look at here. And the first thing that you want to look at is if your integrand is of the form, let's say c over x squared plus a squared, then you can use the fact that the integral of 1 over x squared plus a squared, this is something we talked about very recently, it's an inverse tangent. So that's one thing you want to look for. Another thing you want to look for is you can see if you can split up the function. So, these are kind of overlapping with some of the earlier rules that we wrote, but I just want to mention them because I think recently we've learned that you can do partial fractions with rational functions, but I want to make sure that you are thinking about the easier methods before you start thinking about rational functions. So when I say split up the function if possible, I mean something like this. So let's say you have the integral of 5x plus 3 divided by x squared. You can split this up into the integral of 5x over x squared plus 3 over x squared, right? And just go from there. Another thing that you can look for before resorting to partial fractions is to try a substitution. So that might look something like the following. So if you have the integral of, let's say, 2x over x squared plus 9. Well, if you let u equal x squared plus 9, then du is going to be equal to 2x dx. And so you'll be able to get rid of that 2x in the numerator. And then if none of those things work, so if it's a more complicated rational function that you can't just use one of these, then you want to use partial fraction decomposition, which we talked about in the last couple of videos. And basically, once you use partial fraction decomposition, then that's going to put you in situations where you can now actually apply these first three things, right? It'll break it down into pieces that kind of look like one of these three, or even kind of simpler rational functions. Okay, so one other type, two more types. So the next type of function I want to talk about is, C, a product of multiple types of functions. And then another situation where you're going to use this method would be an integrand involving ln or inverse trig. So examples of, or what would you do in that case? You would use integration by parts. So just to remind you what that might look like. So a very typical example of an integration by parts problem might be something like x squared times sine of x. So remember, you're usually setting u equal to the thing that gets more simple when you take its derivative, not always, but usually. And so in this case, you would be setting u equal to x squared and dv equal to sine of x. So that's like a very typical example of an integration by parts problem, but you can also use integration by parts for integrals involving ln or inverse trig, even if it's not actually a product. So an example of that might be the integral of -3 times inverse sine of 5x. So what would you do in this case? Well, you would let u equal -3 times inverse sine of 5x, and you know, maybe you would pull out that -3, and then you would let dv equal 1 dx. So sometimes, remember, there's this thing of basically taking your whole integrand and setting that equal to u if you know how to take its derivative, and then just letting dv equal 1, because then the antiderivative of that will be x. All right, last type of function that you might encounter is a radical. So we talked about, and so when I say radical, I mean like a square root. So if you have a function that contains one of the following expressions, so the square root of x squared minus a squared, the square root of a squared minus x squared, or the square root of x squared plus a squared, those are situations where you want to use trigonometric substitution. So, you know, we talked in some earlier videos about, you know, how you know which substitution to use in which case. Another thing that might come up is actually a regular substitution. So I'm going to say substitution, but here I mean not trig substitution. So an example of an integral that contains a radical where you would not use trig substitution would be something like this. So let's say we have x times the integral of 4 minus x. Well, if we let u equal 4 minus x, then we could also write that as x is equal to 4 minus u. And then du would be equal to negative dx. And so we could rewrite this integral as negative integral of 4 minus u times the square root of u du. And it looks so similar to what we started with, but the difference is that in the first one, we could not distribute the x into the square root, but now we can. Now we can distribute the 4 and the negative u. We can multiply those with the square root of u and then just use the reverse power rule to integrate. Okay, so that basically covers all of the different types of functions you might encounter and all the kind of general strategies that we have. So for the remainder of the video, we're basically just going to do a bunch of examples. And so some of these are going to be fairly straightforward, basically just kind of using the methods that, that we've introduced on this list. And then some of them are going to be a little trickier. So they might involve like multiple steps. So not just doing one of the things on that list, but multiple of the things on that list. All right, so let's start with an example. So let's say that we wanted to find the integral of e to the inverse tangent of x over 1 plus x squared. So thinking about our list of different strategies, we have the idea of looking at our integral table, and if you did, you would see that this is not on there. And then we have the idea of simplification, and this one doesn't really simplify. So if we look back to our list, what's the next thing that's suggested after trying to simplify? Well, it's looking for a substitution. So let's look and see if we can find a substitution to do here. So again, with substitution, you're usually looking for, is there something whose derivative also appears in the integral? And in this case, we can see that we have inverse tangent and we also have the derivative of inverse tangent. And so in this case, what we would do is we would let u equal inverse tangent of x. And then du would be 1 over 1 plus x squared dx. And so this whole integral would just become the integral of e to the u du, basically. I don't even need a denominator, right? Because the 1 over 1 plus x squared is gonna is part of the dx, and then that turns into a du. So like I said, I'm not going to finish off all of these examples. We're basically just sort of talking about how to, decide which method to use. So I'll stop the examples at a point where it becomes, kind of a normal integral that you know how to evaluate. All right, let's look at another example. So what about if we had the integral of inverse tangent of x over x squared? So this one, you might think of like using a substitution, but it doesn't quite work. So if the denominator was 1 plus x squared, then this would work. You could set u equal to inverse tangent of x again. But being that the denominator is just x squared, it's not going to work. No substitution is going to work here. And there just really isn't any simplification you can do, right? So what's the next thing we can think about? Well, this is like, even though it looks like it's a quotient, it really is also a product of two functions, right? So we could rewrite this as the integral of inverse tangent of x times x to the negative 2. And so what would we want to do in this case? Well, this would be an integration by parts problem. And so anytime you're doing integration by parts, if you have inverse trig involved, or if you have a logarithm involved, those are the ones that you're always going to set equal to u. And the reason for that is we don't know the antiderivative of them. So we can't if we let dv equal inverse tangent of x, we'll get stuck. So we have to let u equal inverse tangent of x. So the integration by parts here would be u is equal to inverse tangent of x, and then dv would be equal to x to the negative 2 dx. And so what would this give us? This would give us du is equal to 1 over 1 plus x squared dx. And v would be equal to negative 1 over x. Okay, so let's put this together and see what we get in our new integral. So we would have u times v. So that's going to be negative inverse tangent of x over x minus the integral of v du. So that's going to be negative, so let's make this a plus, 1 over x, I'll just write it like this, x times 1 plus x squared. So what can we do from here? Well, we can actually just do, partial fractions. The word wasn't coming to me. So we can do partial fractions, right? So we can then, and I'm not going to finish this off because we've spent a lot of time talking about partial fractions in this class, but from here you can do partial fractions because the two denominators will be, I'll write this down. I won't finish it off, but we could write this as a over x plus bx plus c over 1 plus x squared. And figure out what a, b, and c are from there. All right, another example. So this next one I think is pretty tricky. So let's say that we have 3e to the 2x plus 10e to the x divided by 3e to the 2x plus 9e to the x plus 20. So what does this function kind of look like Well, it's not a rational function, but it kind of resembles one, right? It might remind you of the ones that we were doing in the last couple of videos about partial fractions, right? Because we're basically adding up different powers of e to the x. So what we're actually going to end up doing here is setting u equal to e to the x. And we'll see that that will give us, we'll basically be able to transform it into an integral where we can use partial fractions. So I want to do one kind of simplification step first. I'm going to factor out an e to the x from the entire numerator. And this isn't something that you have to do in order to get this correct, but I think it will help kind of see why this works. So if we factor out an e to the x from the numerator, we'll be left with 3e to the x plus 10. And then we'll leave the denominator the same. So 3e to the 2x plus 9e to the x plus 20. And then I'm pulling out this e to the x from the numerator. So why did I factor out that e to the x from the numerator? Well, if we're going to turn this into a rational function with the substitution u is equal to e to the x, the derivative of e to the x is e to the x. So in order to accomplish that substitution, we need to have this extra factor of e to the x to cancel out with the substitution. And then I'm going to take one more step that I think will just really kind of help show why this substitution is the right choice. So I'm going to rewrite in the denominator, I'm going to rewrite this as 3 times e to the x squared plus 9e to the x plus 20. So the reason I'm rewriting it that way is just to really show how it's not a polynomial in x, but it's a polynomial in e to the x, right? Because we're taking e to the x and squaring it, and then adding to that 9e to the x and adding 20. So let's do the substitution now. So if we let u equal e to the x, then du is going to equal e to the x dx. And so that's where this whole thing is just going to turn into du. So now we're going to have the integral of 3u plus 10 over 3u squared plus 9u plus 20. And then, like we said, the e to the x goes away, the one on the outside, and we have du. So if you hadn't noticed that you could factor this out, that's okay. Basically, you would have this extra e to the x, or sorry, not there, but you would basically just be able to cancel it at this stage. Yeah, no, you would have an extra e to the x in the denominator, and then you would have to cancel that out with the extra e to the x that would still be in your expression. So it'd still work. And then from here, you can use partial fractions. And so this example is actually from one of your worksheets. So I think it was the worksheet from the first video about partial fractions. And so it would go exactly like that. And then the only change you'd have to do is at the very end, you would have to put back in e to the x instead of u. All right, next example. So let's say now that we wanted to do the integral of sine of x times cosine of x times e to the sine of x dx. So in this one, you can kind of see that there might be a substitution going on, right? Because we have an exponent of sine of x, and then we have the derivative of that here as cosine of x. However, we also have this extra sine of x. So what's going to happen with that? Well, if we let u equal sine of x, then this will also become a u. So let's just kind of see how this plays out, and then we'll see what the next step would be. So if we let u equal sine of x, then du is equal to cosine of x times dx. And so that means that we can get rid of those and replace them with du. So now we're going to have the integral of u times e to the u times du. And so where would we go from here? Well, now this is an integration by parts problem, right? So we would do integration by parts, and specifically we would so now we would need to use new letters. So maybe we can call them w and v instead of u and v. So you would let w equal u, and you would let dv equal e to the u du, and go from there. So basically we just saw two examples that were kind of along the same lines, right? The first one that we just did, we did substitution, and then after substitution, it became partial fractions. This is one where first we did substitution and then it became integration by parts. So basically, if you see a substitution that might work, go ahead and do it, and just be aware that there might be another step after that. And it doesn't mean that it's not going to work. It just means that there might be something else you have to do after doing the substitution. All right, one more example I want to look at, and this one is, I think, particularly tricky. So what would we want to do on this one? I mean, nothing really jumps out, right? Because we don't see, like, you might think of substituting out x plus e to the x, but then you don't really have a d, like when you take the derivative of that, if you let u equal x plus e to the x, then du would be 1 plus e to the x, and you don't really see anywhere for that to cancel out or go. So on this one, we want to do a trick initially of rewriting the integrand a different way. So remember that when you have exponents that are being added, you can rewrite that as multiplication. So we can rewrite this as e to the x times e to the x squared. Or sorry, I don't know where that came from. Times e to the x, my bad, sorry. So all I did was I took this exponent, and because it's addition, you can rewrite that as multiplication. And so now you might see that there is a substitution that will work, because if we look at what we have here, we have an e to the x in the numerator. That's kind of in the exponent. That's kind of the most complicated thing that is in this integral, right? And then the derivative of that is e to the x, which is right here. So if we let u equal e to the x, then du is going to equal e to the x dx. So there's our du. And so we can rewrite this integral as the integral of e to the u du. And then, then you can take it from there. So, sometimes this isn't going to come up so often, but, sometimes there's just a kind of a clever way to rewrite your integrand that will allow you to, jump into the methods that we've talked about in this video. All right, one last thing I want to talk about. It's not going to be more examples. It's going to be actually examples that we don't know how to do. So there's just one thing that I haven't really talked about too much in this class that I think is worth mentioning, which is that there are a lot of functions that actually cannot be integrated using the methods that we've learned in this class. Basically, they're functions who their antiderivative cannot be expressed in terms of the functions that we know. So I just want to give a few examples of seemingly simple functions that actually cannot be integrated. So basically what I just said is that there are many seemingly simple functions whose, it's not to say that they don't have an antiderivative, but their antiderivatives cannot be expressed in terms of the familiar functions that we know. So you can't, express the antiderivative in terms of sine or cosine or a polynomial or a radical function or inverse trig or any of those, all the types of functions we've been working with. So you have to resort to other methods, which we are not going to be covering in this class. So I just want to show you a few examples of functions that actually we can't integrate. So examples would be e to the x squared. That one cannot, the antiderivative cannot be expressed in terms of the functions that we know. Another example would be e to the x over x. Another example would be sine of x over x. Another example would be sine of x squared. And then last example I'm going to give you is 1 over ln of x. So all of these look pretty friendly, right? There's nothing too complicated about them, but as hard as you might try from the examples we've learned in this class so far, you're not going to be able to do them. And it's not just because we didn't learn enough, it's because really the antiderivatives cannot be expressed in terms of familiar functions. So the reason I'm telling you this is basically, I don't want you to have the wrong idea. I think in this class, it kind of feels like we've learned how to deal with all sorts of types of functions, but really that's because you're being handed nice functions. They might look complicated to you, but you're actually being handed in this class fairly nice functions that actually can be integrated. But I just want you to be aware that there are many functions out there where you can't do the methods that we've learned on these functions. All right, I will see you all in the next video.